Okay, we're going to continue the MATLAB Bootcamp 3, looking at the second case study, which is also a chemical reactor, but it's quite a bit different from the one that we looked at with ammonia. This example is taken from Scott Fogler's kinetics text, which is denoted at the bottom of this slide for a particular edition. And it deals with the cracking of acetone to ketene and methane. And a couple of significant differences we've got going on here. First, this is not a flow through a packed bed reactor, but through tubes which are vacated. So it's just approximated as a plug flow reactor. And the reaction itself is highly endothermic, so that if you try to run the reaction adiabatically without the assist of any heat transfer, it very quickly shuts itself off as the temperature goes down rapidly. And so the configuration of this reactor is that it has many small tubes. In our configuration, 1,000 1-inch tubes. And around these tubes, it has countercurrent heat exchange with a flow of air. And what that means is that the air obviously comes in at the exit of the reactor tubes, comes around the reactor tubes, and the air exits at the location where the feed of acetone comes in. So we're given some basic data here and operating conditions for an industrial scale reactor. And in the end, what we can do, as noted by reducing the feed to the feed per tube, is that we can end up modeling a single tube, and then we can take the results of that and scale it back up to the overall reactor size by using the factor of 1,000. Since these tubes are open, we assume that the pressure drop through the tubes is not significant. You can see the tube length is about 3.6 meters. And this is where we start. You'll notice the inlet air temperature is 1250, and that is the temperature of the air as it enters the reactor at the end where our reactants exit. Okay, so I've just included here a picture of what one of these reactors might look like. It's not the actual one that we'd be dealing with here, but the idea of having these reactors with a large number of tubes and having heat transfer associated with the outside of the tubes is a common configuration for certain chemical reactions. So it turns out that in many ways, the model for the reaction and reactor is relatively simple compared to the one we were dealing with ammonia, which was at elevated pressure. And so here we've got the first order kinetics and given a reaction rate here described by the natural log can be converted to standard Arrhenius type expression. And the rate parameter, and here the time scale is in hours. So we keep that in mind. And then we've got some other property data where we are able to get this from a source like NIST. And this is the heat capacities of our three components as a function of temperature, where temperature is the temperature in Kelvin scaled by 1,000. And then we have our formula for average heat capacity here in the middle. And then we can scale that to our TK, scaled temperature, by including a factor of 1,000 here. The heat of reaction, a little bit small on the slide, but it's 80,770 kilojoules per kilomole. And then that's at 25 degrees. And then we can adjust the heat of reaction to the reaction temperature by using essentially the changes in enthalpy from standard a reference temperature for each of our components. And each of the components, that change can be described in terms of their heat capacity. So things aren't getting too complicated here. The feed concentration, if we take that and want to compute that for our kinetics, we can get from the ideal gas law. And here we're using the ideal gas law because we're not operating at an elevated pressure. The pressure is about 1.6 atmospheres. And so the ideal gas law would be relatively valid. And so we can calculate, for instance, the feed concentration in terms of kilomoles per cubic meter. All right, because that feed concentration is all acetone. And then we can do our balances as we did in the previous example, where we've got a molar flow rate of acetone and we show its first order, all right, disappearance using the rate. And then we show how we can come up with the concentration, all right, using our relative flow rate times the concentration at the feed conditions and adjusted by the temperature change, these temperatures being in kelvins. Then the molar flow rates of the ketene and the methane, since it's equimolar, are given by the difference in molar flow rate of the acetone from the feed. We can have the total feed here. The energy balance is relatively easy to deal with here in terms of the enthalpy that we have in modeling the heat transfer. And we have that enthalpy being that of all three components. And here's one example of how we get one of those. And then for the air, the one thing that we notice here is that since we're dealing with countercurrent flow, we have minus V here in the differential, so that when we move the minus sign out, it gives us TA versus T over here on this side, with the same type of relationship here for enthalpy, okay? And then we can again go to an information flow diagram. to show how we come up with a full model description. And this is where we are allowing heat capacities to be variable with temperature. A similar type of arrangement, what we had with the ammonia reactor, although simpler. And we have here differential equations in terms of the enthalpy of our reaction mixture and the enthalpy of the air. And then we have our main differential equation for the acetone disappearance. And we have our stoichiometric relationship and total flow relationship, and computing again the concentration of A to go in here. And that requires the temperature, as does the Arrhenius expression. So where do we get the temperature? We get it from, as we have before, by solving the enthalpy balance for temperature, which is a nonlinear algebraic solution. And we solve the enthalpy balance for the temperature of the air. And once we have those two, we can put them into our two differential enthalpy balances and use numerical methods to solve that. So that's what the nonlinear model would look like. Then we can consider, well, what would happen if we made some simplifying assumptions. And here we take a look at what those simplifications would be. We can take our differential equation for enthalpy, and we can describe the derivative here in terms of the individual enthalpies, and that gives us, by the product rule, these two summations. The flow rate of a component is given by the rate of reaction, which would have a coefficient, stoichiometric coefficient. And then we can take each of the HIs and simplify them by assuming constant heat capacity, to a derivative in volume. And that then brings us back to taking these two expressions, substituting in these two, and coming up with this for our model for the enthalpy of component I. Using then our stoichiometric coefficients, we can use that to come up with the heat of reaction, and that goes into our balance, which gives us a derivative in terms of temperature and not enthalpy. So that's the major simplification. And then likewise here with air, we make a similar type of change, and we come up with a differential equation in terms of the temperature of the air, assuming a constant heat capacity, and our flow rate, molar flow rate of air, does not change because there's no reaction there. So if we put that into a model, it's somewhat simplified now, and we have a differential equation for the molar flow rate of acetone, one for the temperature of our reacting mixture, and one for the temperature of the air, and then we just have these supporting relationships here. So now we need to talk about a solution strategy here, because we have a countercurrent system, and you may remember the countercurrent tube-in-tube heat exchanger from our Bootcamp 2 example. And so we develop a solution strategy that looks like this. And that is, we estimate the final air temperature at our initial volume where the air exits. And then we solve our model forward to the exit of the reactor, and we determine the air temperature there from the solution. Now, the air temperature there has a specification of the inlet air temperature, which is 1250. So we have to check and see whether our estimated air here gave us an exit air, a final air from integration, that meets our specification. If it does, we're done. If it's not, we have to come back around and we have to re-estimate the final air temperature until it does meet this condition. And for example, in Excel, we can use the solver to do this. In MATLAB, we can use a built-in routine in the optimization toolbox called fmin UNC. So that's the general strategy that we have. Now we're going to lay that out in a diagram and create the code in order to do this. And even though our model is simpler than the ammonia model, the strategy that we need to put together to solve the two-point boundary problem is more complicated. So this is the general strategy that we have. And that is that we have a main script which produces an air output temperature, and then that goes to our ODE 45, which solves the model and determines the air feed temperature at the end of the reaction, and then comes back around and adjusts this until we meet the specification. The routine we use to make adjustments is this built-in routine in MATLAB, and what it uses is a sum square of error criterion between the computed air temperature at the end of the reactor and the specified, and squares it. And then we go to solving the model, all right, with the new estimate of TA0, and we continue that until we have converged. So this initial script is actually quite simple, and what it says here is that we set some options for optimization, and we say that we're going to be using this particular routine, and then we come in and we solve the problem using fmin UNC, and we'll see how this works a little more later on, and when we're done, we display our result. So let's go over and look at some code with the editor. Bring up the command window first, and then the editor. And let's take a look at, see if we're in the right directory here. I don't think we are. So we'll get in our Acetone PFR directory, and then we'll come over to our editor and we'll do open Acetone PFR Simplified. So this is the routine that solves the simplified model. It has a similar organization to what you've seen now several times, using a lot of comments. We have some basic data here that we specify. These are the geometric data for the reactor. Here we have like the molecular weight of acetone in air. And then we come down, we've got a heat transfer coefficient that we've had to estimate or come up with from a correlation. And then we've got an area per length of tube, heat transfer area per length of tube, and that in this case is meters squared per volume meter cubed, and net units are meters to the -1. And then we have our operating conditions in terms of our acetone feed, temperature, pressure, and we have our air feed, all right, and with the appropriate temperature. And here we estimate the air temperature as it exits the reactor at V equals 0 at 1120, and we know we want that to be at 1250 when we finish solving the model. So the TA0 is just an estimate at this point. Then we come down and we set V-span for 200 points for one tube, and we have initial conditions of the feed, the temperature, and the TA0 for the temperature of the air as it exits the reactor at V equals 0. Temperature of the feed is TF. As you've seen now many times, we declare an anonymous function in terms of volume and our dependent variables, and reference PFR acetone simplified with those and some additional parameters that we need to pass through from here through ODE 45 in this case to the PFR acetone simplified function. So let's go take a look at that. So this is PFR acetone simplified. It's not that long a routine. As again, we have our V, we have our dependent variables Y, and we have our extra arguments. And then in this particular case, we specify our heat capacities here, all right, in our kinetic parameters. And then we unpack our Y variables into the flow rate of acetone, temperature of air. We compute using stoichiometry our flow rates for ketene and methane, and then our total flow rate, molar flow rate. Then we have computing the concentration of acetone, as we've shown before, our rate of reaction, and then we have our derivatives. In this case, we do not have any algebraic expressions that we're trying to solve for along the way. We've not done it that way. We only have derivatives, and for that reason, we don't need a mass matrix, and we don't have to use ODE 15S along with that. So we used ODE 45, a conventional integration scheme. So the first derivative is disappearance of acetone. And then we've got the sum of our flow rates times heat capacities. And then we have our differential equation for temperature of our reaction mixture divided by that denominator. And then we have the differential equation for temperature of air. We have the three derivatives, we transpose them and return that from the function. Let me go back to that for a moment. You'll notice that we have a function here for heat of reaction. So let's open that up and take a look at it. And this just computes the heat of reaction, taking the temperature, converting it over to the kelvins, and then dividing by 1000, all right? And so goes through the calculations here for the enthalpies using that factor of 1,000 that we introduced here for this one. And then it computes the enthalpy heat of reaction by taking the initial enthalpy and then accounting for the changes. So that's the heat of reaction. Let's come back to our main script. We solve the equations, get our 200 points of volume in all of our dependent variables. We unpack them, right? And here we unpack acetone and then just calculate based on an array of acetone. We just calculate the ketene and methane corresponding flow rates. We have our temperature profiles. We calculate our conversion, and we do this here not in percent but fractional, and then we make 3 plots of our acetone and ketene. Methane would be the same, and temperature of the reaction mixture and of the air on the same plot, and temperature of the a plot of the conversion versus volume, and finally we make a display on the command window of the air entry temperature at the end of the solution. So that's what that looks like, okay? So let's just take a look at what happens when we run that model. Okay, so we get a conversion profile, and what you can see here is that the reaction goes to completion at about 1.8 1.8, all right, cubic meters, all right, and then that's for an individual tube, or 1,800 if you're talking about the overall reactor. We've got our temperature profiles where we started with our 1120 initial estimate. And so this is the reaction. You'll notice that the endothermic nature takes us down a bit, and then with the heat transfer from air, it brings the temperature back up. And you'll notice that our air entry temperature, air's coming in this way, is not at 1250. So we have not met the requirement for the 2-point boundary value problem yet. We're off a bit. So we have our molar flow rates for acetone and ketene, acetone being depleted, ketene being created, all right? So that's what that looks like. And now what we're going to do is we're going to focus on how we go about solving the 2-point boundary value problem, all right? So let's pop over to the slides and catch up to this point, and then we'll move on to the 2-point boundary value problem. So here's our slide. This is the main script that we went through with you. Not going to go through it again. And it finishes up with the plots and displaying that final air temperature. And then we've got our model to compute the derivatives, our heat of reaction routine, and then we have our temperature conversion profile showing that we don't quite hit the target for the entry temperature of air. And then we have our molar flow rate chart, okay? So let's pop back over to here, and it shows you that the air entry temperature is 1260, which is, it should be 1250. So we're off by 10 degrees. And so we will bring in that routine that is called solve 2-point boundary value problem. this one here, okay, and that we discussed before. And here, what we're using for this is we're using F-min UNC, and it's getting its performance value from SSE. We'll look at that. And it's starting with a value of TA0, all right? And then we've set some options here. So if we want to find out more about F-min UNC, we can come over here, put it into our help window, and it's in the optimization toolbox, and it gives you your full help description along with examples of how to use it, all right? So that essentially should find the right value of the TA out. And here it's using an initial estimate of 1050, which is way off. And then it ends up giving us some additional information along with that. And in this case, we just display the TA out to show the final result. Okay, so that's that. And we come in and show the SSE now. So here's the SSE, and what we want that to have here is solve PFR simplified. All right, that is the routine that we're after. Later on, we'll remove the word simplified when we solve the full model instead of the simplified model. And it gives a performance measure, which is returned as the difference between the computed TAF and the target TAF, and we square that. So it gives a performance criterion that will always be positive or approach zero. And that's what the F-min UNC wants to see and work with. So now we need to look at solve PFR simplified. So we do that. Here it is. And again, this looks very much like what we had for our main script before, except now it's a function and it starts with an estimate of TA0 and it returns a TAF, which is at the full volume of the reactor, the inlet temperature. So that's what it does. It goes through the same type of specifications that we had before, all right? And then instead of all the plots and everything, it just comes along and it determines the final value of TA out to return, all right? So that's what that does, all right? And in solving it, it is solving PFR acetone simplified, all right, which is the same routine that we used before, all right? Let's come back to that. Sorry. It's integrating the model from PFR acetone simplified in order to get the results that we need, all right? And so if we come back to the solve two-point boundary value problem, and that is our main script, and we ask that to be run, it's run, all right? And what we see here is it gives us a temperature of 1,112, roughly 0.9. All right. So if we wanted to say, well, how does that show with our plots, we could come back and with our original simplified model, we could put an initial temperature here. What was that? 2.8, was that correct? 1112.9. Let's make it 0.9. And then we could take that and we could run that model to see our charts. And this is roughly the same as before. And now we notice our temperature profile hits the 1250 requirement right on the button. So that's how we have solved the 2-point boundary value problem. Okay? So having done that, we're going to look at our slides for a moment and say that here is, and this comes back to that solution scheme that we had on the one slide, the solve using FMIN-UNC, which requires SSE, and the SSE uses the solve PFR simplified, which is this particular set of code, all right, and returns that air, essentially at the end of the integration, the entry air temperature from the model solution, and then it shows that we get the correct result for that, okay? And we have our molar flow rate chart. So now, just for a moment, what we want to do is go back and see what happens when we solve this for the full model instead of the simplified model. So we'll come back here to our editor and we'll go over to our SSE, and instead of using solve PFR simplified, we will just use solve PFR. So we're no longer using solve PFR simplified. So we need to bring in solve PFR, just down here somewhere. Here it is. This routine looks very similar to one for the simplified model, at least with the beginning of the script here, setting our basic data, reactor dimensions, heat transfer parameters, operating conditions in terms of the feed rates, and then things change because what we're doing here is we're setting initial conditions in terms of the H values for our reacting stream and our air stream, and needing for the reacting stream the heat of formation of acetone to give us our initial value here. And then the same in terms of setting our V-span, but now the initial conditions are in terms of the molar flow rate of acetone and then the two enthalpies according to our model information flow diagram. And then coming down here, we are using a routine called PFR acetone and not the word simplified in there. So let's go take a look at that. One that computes our derivatives for us. And the main difference here as we come down through here is that we have our two functions, find T and find TA, that use the enthalpy data in order to find the temperatures using what we call the algebraic loop. So if we take a look at find T, let's open that. What we see here is a typical while one loop to implement the modified secant method, the variation from Newton's method, where we come in with an initial estimate of temperature. And one of the arguments is the current value of the enthalpy, H. And then we perturb the temperature a little bit by 1/100th of a degree and use the modified secant formula to obtain a new value of the temperature. And then we'll exit this loop when the new value is not changing very much from the old value. And this makes use of a function that computes that block on the information flow diagram. The function is called FH, so let's open that one. And so this essentially takes our temperature and computes our enthalpies, adds them together and subtracts them away from the current value of the enthalpy. And what we want to do is have our modified secant method drive this to zero, so we're using the current value of the temperature, and that resolves the temperature for us. You can see that this uses functions to compute the heat capacity, the average heat capacity of our three reacting components. So if we'll just open one of those for acetone. And this is just a fairly standard procedure for taking our temperature and then reducing it by 1,000 and putting it into our formula for the heat capacity and average heat capacity calculation, where these are integrated terms in terms of temperature. And so that handles that for us. And if we come back to our PFR acetone, we have a similar calculation to find the temperature of the air. So let's open that. Find TA. And this again is same type of scheme with modified secant method. We're using now a function FHA. We'll take a quick look at that. And this is a similar type of thing where we are comparing the current enthalpy of the air to that calculated by using the current estimate of the temperature. And our modified secant method will work until these two equal each other, and then we have determined the temperature of the air. So that, apart from that, we have computing the concentration, the rate of reaction, and then our three derivatives, where the second and third one are for the enthalpy values of the reaction mixture and the air. So that is, including all those supporting relationships, is pretty much it. What we can then do is solve the model using our solve two-point boundary value problem. Same type of approach using F min, U, and C, and solve this, run it, and it thinks it's solved. Let's go to the command window And it says here that our stopping criteria is met and that the correct estimate for the outlet temperature of air, which occurs at V equals 0, is 1117.7. And I think that is only different in the fifth figure from what we determined from the simplified model. So if we have 1117.7, we can then come back and open up our acetone PFR script, which solves the model, and come down here, and instead of using an initial estimate for the air temperature of something like 1125, we can put in 1111.7, and let me check that. 1111.7, okay. 7.7, I'm sorry. Put that in and run this particular model, and it gives us our conversion profile, very similar to what we saw before. And then it gives us our temperature profiles, and you'll notice that we have met the requirement for the entry temperature there at 1250, okay? So this is using the same type of approach to determine the two-point boundary value problem and solve for that using the FMIN-UNC routine. Same thing that we did with the simplified model. And we could have gone on here to do what we did with the ammonia models, and that is develop a comparison script so we can take a look at the differences. Since we know how to do that, I'm not taking the time to include that here. So let's come back over to our slide presentation and complete the workshop here. So this was the SSE routine, now with the solved PFR, not with the word simplified. This is the solved PFR, which takes the estimate for the air outlet temperature at V equals 0 and returns the final value, the entry temperature of air. And this just goes through the code that we reviewed. And you will notice over here, whoops, let's come back over. You will notice that the anonymous function here, well, first the initial values are molar flow rate of acetone and our two enthalpies now. And then we have our PFR acetone that we reviewed with you. Then when we get the solution, we unpack that first in terms of the molar flow of acetone for our 200 points. And then we use the stoichiometry to get the 200 points for ketene and methane. And then we come back around and we use our fine T and fine TA to convert all of our enthalpy values for the reaction mixture and air into an array for all of the temperature values. And then having that, we just return TAF as the last value of the air temperature. And just an editorial comment for here, we really don't need this code here for the reacting mixture because the function is only interested in returning the final or the air temperature at final volume, okay? And then this was the derivatives, computing the derivatives with the PFR acetone routine, and we pointed out how you use the fine T and fine TA to resolve those two algebraic loops from our information flow diagram. And this was the one for find T. This was the one for find TA. And then we have all of our heat capacity routines. And finally, we have our acetone PFR model so that we can put in our temperature that we determined from solving the 2-point boundary value problem. And in that way, we can get our profiles, all right? And here is the graph of the molar flow rates. And the results are actually very similar between the full model and the simplified model. So this brings us to the end of our MATLAB bootcamps, 1, 2, and 3. I hope they've been helpful to you. I note here the references with Scott Fogler's text and Steve Chapra's text, and my contact information should you need any help going forward. Thank you very much. I will also mention that there are similar bootcamp series for Python and for Excel with VBA, should you wish to explore those. That's it for now. Goodbye.